When we are dealing with small objects, we use some kind of microscopes to look at those features, to measure those sizes at those small scales, and even to characterize their interaction with the underlying substrate. When we make nanoscale objects, nanoscale features, or we have a design of some kind of device that goes into micro or nanoscale, we also again use microscopes. Now, microscopes at those size scales are not optical microscopes like we are used to uh, on desktop in high school or in college. But these are microscopes which are called electron microscopes or probe microscopes, scanning probe microscopes. So essentially, in electron microscopes that uh, we are using electrons or a beam of electrons or even ion beams to look at the features or look at the objects of the surface. Now, like in this picture, it shows optical microscope where we have a light source, and we may have our objective eyepiece on the lower side, on the other side, or maybe it may be on the same side. But in any case, we have bunch of optical lenses that we use to focus our light, to focus the uh, image that's coming through those lenses, and we go up and down to align the focal plane with the focal length. So hence we can see an image which is in focus. In electron microscopes, there are two major types. One is called TEM, which is transmission electron microscope, and another is scanning electron microscope. So principle is very much the same, but now we are dealing with electrons and electron beams. So in this case, we use magnetic coils or coils. So we have to basically move the charge electrons, right? So electron moving, and they have vacuum in those columns, in those tall columns. What we do is we project those electrons in a very, very fine, very narrow kind of beam. And that beam, when in case of transmission electron, when that beam goes through a thin sample, we can see the features of that sample. It has to be very thin. Now, those features, a lot of time we look at the atomic scale kind of a configuration. So we look at diffraction pattern. But for very thin samples, we can look at the samples, and we can see crystalline structure there as well. For scanning electron microscope, we would scan a beam of electrons on a surface, and we see electrons that are backscattered or electrons that are emitted out of the surface in response to those electrons that are striking those electrons within the surface. So that's an many times it's an elastic kind of collision. So we are looking at electron interactions with the substrate. So that's for electron microscopes. When you get to scanning probe microscopes, they have slightly different uh, behavior or principle. We'll get to that. Now, electron microscopes were developed long time ago, and the first commercial one was sold in 1965. So here's a picture of a 100 kilovolt SEM from, well, so you can see from this picture that it's kind of a column. So you have the electron gun at the top, and there's that interaction of that electron beam as I showed you in previous slide. So we are essentially, we have gone through many iterations. Today we have very sophisticated electron microscopes that can fit kind of a briefcase. So you can carry them around. They are uh, become so small and compact that portables that you can put it on a desktop and start looking at it. So this is an example on the right hand side of a transmission electron microscope. So so microscopic people, they like to call them columns. So in their language, they call them column. So you can see there's electron gun, the word says electron gun, and then a bunch of, we call them lenses. So they're basically electromagnetic coils. So their job is to uh, bring those scattering electrons into a very tight beam. And once they get to the substrate, to the material under investigation, device under test, so which would be, it's a specimen block. So it would be somewhere here. And electrons would strike and go all the way down. And here is where we would get the main screen, where we would get the image that's made there. And from there, you can either look at that image directly. There's kind of a window here. You have to remember that this whole column is under high vacuum. So very, very tight control inside this whole body, where electrons can move without any uh, uh, collisions with any particles that would have been there if it was not under high vacuum. So it's a tightly closed in chamber of the whole microscope. So there is, of course, so TEMs have also gone through many iterations. So they have very fantastic tools which do not take too long to operate. Uh, Basically, the the we don't even have to pump them down to ultra high vacuum nowadays. So now this just the comparison, that one requires a conducting sample scanning electron microscopes because we have to see the interactions of electrons with the substrate. And TM requires a very thin substrate, a very thin sample. And they both are operated in vacuum, or now vacuum is again, now we have some microscopes, what we call them, they are environmental microscopes. So where you don't have to pump them really high, but we still have to clean the air so we can get rid of any particles in the air. Now, here are some examples of SEM images. So as you can see, the images are grayscale because what we are looking at is the electrons that would strike and they reflect backscattered or OJ electrons. So a bunch of kind of electrons that would strike on the surface, reflect back, and we look at those. So some examples of very fine and high resolution images. So here there are some nanoparticles, here are some uh, gold on silicon dioxide where you can see very small junction. It's just a metal wire here that's shown in this image. And using these equipment, not just to image, we can also use these to write features on a material coating, what we call E-beam photoresist. So similar fashion, we have a tight spot of electrons and we can write into that E-beam uh, resist, which is a polymer coating, and we directly write with electrons. And we steer the beam, or we can move the stage as shown here on the right hand side, and we can transfer the pattern from the VLSI design or any modern design into a very fine uh, patterns. Now, there are electron beams guns and there are ion guns also. So we call what you call focused ion beam. So those machines are called focused ion beam, FIB, FIBs. So they use same principle. We image with them as well, but the main idea is to use ion beam to do lithography, to write pattern on the surface. So here again, you can have, these are ions, these are bigger particles, they are charged and they would have more energy. And then depending on what are the applications, you can have we have different choices from heavy ion systems or light ion systems. With e-beam lithography, there are many things where they can make patterns of just something that can be used to do the standard kind of silicon processing, or they are used for devices where we can put bunch of organic molecules or biological molecules as well, and we can pattern different molecules on the same substrate. Here are some more examples of electron beam lithography from this nano letter paper. So you can see that these patterns, they give high versatility, different angles and the different shapes, different sizes that can be made by using electron beam lithography. So here are, you see there it says backscattered electron image or secondary electron image. So there are two, three types of electrons that once your E-beam strikes, that those electrons are emit out of that substrate, which we can look at various electrons and that can give us an image that's there on the surface. Some more examples where very, very intricate designs have been made, steps, circles, uh, different edges, patterned, tapered edges, and so on and so on and so forth. There is so you can make devices which would give you few atoms kind of thickness. Now going back to the other types, which is called scanning probe microscope. So the idea is there is a probe. There is always a kind of a very fine needle structure which may be moving on the surface substrate. Now this needle may be in contact or it may be slightly away from the surface. So the idea behind scanning tunneling microscope is that there is a very, very fine tunneling current that maybe would be traveling from the tip and the surface. So, but the idea behind tunneling is that it's not in contact, but we can maintain that tunneling current. So the two types, constant current mode and constant height mode. The idea is that we measure that current and that current would help us maintain a specific distance, or if the current changes, we will know if current increases, which would tell us that surface is becoming closer to the tip. If that tunneling current increases, we'll know that it's going away. So that can be used to map the, the sample surface in a computer, depending on where the tip is at what time. So this is basically what we are seeing here. The tip on a surface, it's traveling. Now, if it's going up and down, so that current is being measured, and from the measurement of that current, we would want to keep the same current. So which means we have to move the tip up and down. So that movement up and down is what we would measure. And from that, we can reconstruct the image on the display from whatever the movement of the tip has occurred. So this is the idea behind the basic that and again, there are two operational modes of scanning tunneling microscope that is used to image a surface. With the STM, if you are maintaining a constant current, so there's voltage, so we can use that voltage to manipulate atoms. So this is from a 1993 remarkable report from IBM where they were moving single atoms into various places wherever they wanted to move them. Now, the other type, atomic force microscope. Now, scanning tunneling microscope, STM, is looking at the tunneling current. But atomic force microscope is just mechanically dragging on the surface. So this is from this book. And the principle is that it's a very fine tip and it's suspended. Uh, it's a suspended cantilever and there's the tip. Now, if you're dragging this whole thing on a surface, we would be able to see very fine change into up and down change into this beam depending on whatever the tip encounters at the edge when it's dragging on the surface. So if we can find that, we can reconstruct the image. So because we are moving it in a very controlled way, it's scanning on the surface, and we know X location, Y location, and Z location comes from when this cantilever goes up and down. Now, its up and down movement is measured from a very precise laser and how the laser is reflected back. So there are 4 photodiodes that can measure what is that beam doing. So there's just a small cartoon that if you have 4 photodetectors A, B, C, D, you can exactly know and see how that beam changes between those A, B, C, D, 4 of those. Now, since atomic force microscope is a physical contact, so this has been used to do lots of biomolecule manipulation as well. So where you can coat the subsurface of the tip and use that to uh, drag, to push the proteins out and even find the binding constants of different biological molecules using AFMs. The basic principle of AFM or basic parts of AFM is that it's essentially a semiconductor tip on a cantilever. There is a scanner, piezoelectric scanner, so we can precisely control the movement in X, Y, and Z as well when you bring the sub sample in contact with the tip. And deflection is measured by a spot uh, with photodiodes, and then there's a computer system that can construct the image of from that height change and the XY movement of the tip. So we can measure the topography of surfaces with that. Now, there are repulsive or attractive forces. So the tip is so thin, so there would be some very fine forces that become uh, very active at nanoscale. So those forces then tell us that what is the surface topography. And that's what is fed to that computer system to recreate the image. Right? So this again, a old report from IBM where they were manipulating atoms with scanning probe microscopy. So if you look at the very edge of the tip, so this is just showing that if there is a nanoparticle, when the tip will come, it will be dragged up and it will stay up as long as it doesn't cross, or it can be used to move that particle away with the with that tip. Essentially, what they did here to move the atoms in their specific location using the tip.